Hi, everybody. Thank you, beautiful people in the room. I think we have more people in the crowd than panelists, so that's good. That's already a successful panel here in my attendance. So we're here together today to talk about zkVMs. We just checked right before. There are actually 25 zkVMs, some of them quite unknown actually. And today we're going to talk about whether that's too few or too many, and also maybe some more technicalities about it. So let's start with introducing you guys. I mean, I'm pretty sure some of you guys are quite famous, but let's not only introduce you guys, but also justify why you're here. Maybe for you it's going to be easy, Jacob, because
Yeah, so we're
ReZero.
going to start with the least famous person on this panel. I do believe I have the
You'd
least
be
amount of.
surprised. You'd be surprised. You have quite the
Uh,
following on X.
no, I think I have the least amount of all this. But yeah, I'm Jacob. I work at Risiro. I think people know us for the RIS5 ZKVM at this point, which is getting quite popular. But the second production-ready ZKVM will always give props to Starkware first.
So yeah, maybe we switch then to you, Zach, and
There we go.
I'm pretty sure people here in the room are familiar with Aztec, but also maybe try to focus on why you're here, talking about ZKVMs, and maybe just give a little bit of context, why you basically know about ZKVMs in the with Aztec.
Yeah, sure thing. So yeah, I'm Zach. I'm the CEO of Aztec. We're a privacy first layer too. So yeah, why am I here? Well, I think Aztec's kind of known. Um, for those in the know, Aztec's known for like not really doing much on the VM side, as in we have a language noir which directly compiles to constraints. So I suspect I'm here to kind of like throw some shade and be annoying. Um, we do actually have a zkVM. Was that counted in your 25?
No, I don't think it's on
No,
It's not. Yeah, it's actually 26.
yeah, so the Aztec VM, because we need one for the non-private parts of our transaction flows. So yes, well, why am I here? I mean, I shit post a lot on Twitter. I do a little bit of research. Did this thing called Plonk back in the day, which turned out to be kind of meaningful. And yeah, I think but mostly like what we're focused on Aztec is client-side proving, where we want maximal performance, particularly with regards to resource consumption, which means that for now we prefer the direct compilation method, where you take your program statement and you basically try to find the most optimal constraints without having to go through a VM abstraction.
Yeah, we'll get back to that. But yeah, Maya, up to you.
So I am Maya from Starkware. We built StarkNet, which is a layer 2 ZK rollup. And for that, and even before that, we have the Cairo VM, which is the first general purpose ZK VM. Today you would call it a custom ISA. When we started, it wasn't like there was no standard, so it wouldn't even be considered custom. Yeah.
Yeah, good. Again, we'll get back to that. That's why we're here. But yeah, before doing so, yeah, Alias, maybe say a few words about you.
Hello, guys. I'm Elias. I'm one of the co-founders of Kakarot, and we've been working on proving EVM and blockchain for the past 2 years using Cairo. So we are a ZK EVM, but in the lands of proving rather than rollup.
Yeah, good. I mean, it's actually a good representation of kind of what you do with zkVMs here. We have a good panel, I guess, for that. Well done, the organizers. And we're going to start actually with Jacob. So first, let's talk about kind of the the classic zkVM, let's say. So why? I mean, how is RIS0, working on VMs? Why are you using, RIS5, the ISA, kind of the general purpose, the classic zkVM as we know it, and then maybe we will, find different flavors of zkVM with the other panelists.
Yeah, so RISC-0 is named RISC-0 because we use the RISC-V ISA. Why did our founders pick RISC-V? I tend to use this analogy. RISC-V is like nice. It's used by a lot of people outside of like cryptography and whatnot. And why do people use RISC-V, and where do you find it? The most common place you find it is in tiny computers. Classic example is Raspberry Pi. And why does a Raspberry Pi use RISC-V? It's because RISC-V is terribly simple. There's like 100-ish opcodes. And something really nice is if you don't have that many opcodes, you physically have to use less silica, which is nice if your computer is physically tiny. And that translates to being nice for ZK, because in ZK we have these things called constraints. And if we can build a tinier computer, constraints tend to be closely correlated to prover performance. And if we have to do less constraints, ideally the prover will be more performant. There's a bunch of other things I would say. RISC-V is formally verified. It's maintained by people that are really security focused as well. It never really changes because if you change it, you bork the last generation of hardware, and that's tend to be frowned upon. And then we also get to inherit just like a lot of open source tooling around the RISC-V community. I would say pretty much all of our performance gains either come from two areas right now: GPU bumping, or actually using open source RISC-V tooling for like optimizations, profiling, and sort of doing high performance engineering. And the nice thing also is we get to use Rust, which I think has really grown in the cryptography space. One cool thing there is also is like, yes, does Rust have problems? Yeah. Does LLVM have problems? Yeah. But you look at Facebook, Apple, Google, Amazon, they're actually in the process of changing all of their cryptography backends to Rust libraries. And they're spending, they're going to spend over $100 million solidifying these libraries. So we're going to get to inherit that security as well.
Okay, yeah, I think that makes sense. But now I want to hear from actually Maya, because you just mentioned that actually, Starkware was kind of built a zkVM using custom ISA. So I mean, RISC-V seems like the best thing since like hot water. So why not using RISC-V for you guys? I mean, what was the rationale behind it?
Is this working? When we started, there was no real discussion around RISC-V in the context of zkVMs. There was no zkVM.
In terms of timeline, we're talking pretty much kind of similar years, right? Maybe even before?
Yeah, for 3 years at least, yeah. So the Cairo VM was developed by by Starkware really as a general purpose VM that is dedicated for the task of proving code. So we were not thinking about tooling. When we considered it, we thought which direction to go, and we decided to go for the most performant approach in proving. This comes at a cost. You have to maintain a language and a compiler, and everything has to work. And the Starknet blockchain is written in Cairo or ZK language. So it's a non-trivial way to go, but it's the most performant way to go, we believe. In terms of security, all of our errors, which is the translation from code to proving, basically, is formally verified. We write clean proofs for Stone and for Stu now, our new prover. And we, of course, audit both internally and externally the verifier. So in that regard, I don't think security, well, there's always concerns, but if you formally verify. Yeah, and we see that when we compare the performance of Stu now with Cairo, it outperforms available RISC-V based zkVMs by at least an order of magnitude.
Yeah, I mean, we were actually now already talking about trade-off between like performance and maybe wide usage and like easy DevX basically. And actually, back to you, Zach, you were mentioning that you so you do have a zkVM with Aztec, but went more like the zkDSL way. Is it kind of the logical, like almost like going more in the performance side, like a bit like I guess Starkware did, even going further without actually doing the zkVM?
Well, it's a bit more complicated than that because it's all based around like the targeted execution environment, what we're trying to do, because it's very different. It started out very different to RISC-0 and Starknet, because I think we were kind of Starknet again. Very OG. I was reading papers from Ellie about talking about zkVMs that had like a 1 hertz prover rate, like back from 2015, like, but we got started fairly soon after that, but we had very different focus because back then everyone was looking at ZK for proving blockchain transactions, doing scaling, where the set of kind of operations you want to perform are relatively well understood, as in you know what to optimize for. We wanted to do privacy at Aztec, and specifically why privacy? It's because we wanted to make blockchain mainstream, which means basically touching the real world on chain. And what that really means is getting attestations from Web 2 into Web 3. And that means Web 2 crypto. It means doing things like verifying OAuth within a ZK Snark circuit. It means doing things like verifying RSA signatures for passport proofs, which in Ordnance now we have that, well, not we, but they've built that using on top of our proving tech. And there's kind of this really nasty, ugly, bullshit Web 2 type crypto that's very custom, arbitrarily defined, strange algorithms, and so the path we took was very much modeled on. Honestly, it was I was looking at the path that computing took in the 80s and the 70s, where you have this brand new paradigm, right? Like, wow, computers are a thing, home computers are a thing, learn to code, it's the future. Everybody's like, okay, we need to get on top of this. And so people start creating these abstraction layers to make it easy to program. Programming languages, in the 60s it's Fortran, in the 80s it's BASIC. And these things provide abstraction layers which make the complexity manageable, but they are fucking, sorry for swearing, fucking slow. As in, yeah, you could learn to program computers in BASIC in the 80s, but if you wanted to make a decent application, you needed to write it in machine code. And I'm looking at the state of privacy tech in 2020. I'm looking at what we want to achieve client side, and I'm looking at the technology that we have available, and I'm thinking, if we sped this up by 10x, we sped this up by 100x, we would just what would happen is the applications would become 100 times more complex. It wouldn't become 100 times faster. And what we want to achieve versus the resources we have, the scale is so off that what we should focus on is maximizing the available resources we have at the cost of complexity, and not try to create abstraction layers that will that I thought would be a bit of an anchor around our necks in the future. And so that's why we went the DSL route. Because the thing about, we can probably get into, the thing about zkVMs is they're beautifully generalist, and yes, you can take any program and put them into them, but typically that might be quite slow, right? Like a VM has a lot of overhead because instead of turning your program statement into constraints, you're turning into opcodes, and then you're verifying the opcodes, which means you need a memory trace. It means you need opcode, you need to process individual opcodes. You now have a virtual machine where you're doing loads and you're doing stores, reads, and writes. And if you just directly dump it into constraints, you don't have that. And so, where was I going with this? So we went, thank you. So we're like, yeah, let's just try DSL. Let's just do this the more direct way, where you take the language, turn it into constraints. Our approach to making the complexity manageable was much more at the DSL layer, where we looked at LLVM as an example, where Noir doesn't compile directly to constraints, despite what I've been saying. It compiles to an intermediate representation, which isn't designed to be chunked into a virtual machine. It's designed to be taken by a back-end compiler and converted into constraints. So it means it's modular, it means it's portable, more or less. So you get those advantages, but much like in the kind of the real world, where you have this, you can have directly compiled programs in languages like Rust, or you can have interpreted programs in JavaScript or Java. You have this trade-off between portability and performance, and typically the VMs will always be slower than the directly compiled code, and we thought that would be the same for Snark circuits. So that's the way we went.
Yeah, it's like pushing the zkVM up to the point where it's not a zkVM anymore, basically, because for performance reason, you had to do things differently for clients approving, etc. So yeah, I saw you picked the mic. I guess you want to react to that.
To answer to this, it feels like maybe we're at the very, very beginning of an attempt to blur the lines between VMs and non-VMs, because I think, to the point of Jacob saying people don't change specifications such as RISC-V very often, it's because they're hampered by hardware. In the land of VMs and ZK, you're not really. And the newest designs of provers allow you to add as many opcodes as you want, and they make the ISA very, almost not fungible, but very add-on like, and we saw it because VMs, as you mentioned, Zach, used to be slow. Now they're faster, and they have identified bottlenecks in which that they can offset by building what they call precompiles or specialized chips. But now it feels like we're going to get into an era where there might be we'll see, but it doesn't add so much cost to add a precompile, less formal verification and bugs. But we might come into a place where VMs have extension packages and they are completely fungible between VMs. Kind of maybe, I don't know if this is correct, but maybe like the SIMD extension of ARM. So you might see RISC-V like borrow precompiles from Cairo and then compose at the proof level. So I
have a very different opinion on that.
yes.
Yeah, okay, so I think that I understand why precompiles have come about, and it's quite a natural way of doing things, and I think they are a trap in the way that SIMD was a trap for Intel, not ARM, Intel back in the 2000s, where the idea was, okay, so, it's like was the early 2000s, and Intel's like, this CISC architecture we have is kind of a pain. How do we compete with RISC? How do we get more performance? Oh, I know, we'll do vectorization, right, where we'll do lots and lots of instructions in parallel, and this isn't currently how programs are written, but we'll let the compilers figure it out. That compiler engineers are clever; they'll figure it out. And spoiler alert, they didn't. The compilers engineers looked at this and they're like, "No one uses this stuff. This is really complicated." And that was one of the reasons why that led to, I believe, AMD's first period of domination over Intel, because basically Intel made this decision to do vectorization that was too complex at the time. And so I'm like, this at their lunch. And so what do I think is a trap for the ZK world? It's because precompiles are great until they're not. As in, if you want to achieve completely general purpose compute, but like the fundamental VM architecture is a little bit slow, then it's, if you're like a protocol engineer, right, like building like an EVM prover, right, it's fine to go, ooh, well, Ketchak is slow in this VM and SHA's slow, so we'll just write precompiles for that. But it's not. You're going to random engineers and going, you can build your app in ZK, and their app is slow, and the solution is write a precompile. Because writing a precompile is basically like defining a bunch of custom polynomial algebra. And way beyond the domain knowledge of a typical engineer that's not a cryptographer, not in ZK. And so it's a way of getting VMs to scale for applications that the VM scale, like right now, because it's a kind of a very closed bubble, right, where who the people consuming ZK VMs, they're either are VM engineers or they're very close to it, right? So they can write precompiles, they can figure it out themselves. If you want to get real mainstream adoption, if you want to get Web 2 people starting to use this tech, then the precompile abstraction is going to crash and burn because it's really it's a statement saying only VM engineers, VMs are able to handle the complexity required to speed up applications, and yeah, I don't think that's scalable.
So I think it's not like an either-or kind of situation. So you have people working on ZK VMs, and they can write precompiles for things. Like, for instance, I'm very biased. Like, we write precompiles mainly to support the StarkNet functionality. So we introduce, it's not called precompiles in Cairo, it's just an opcode for the Cairo VM, because we write the VM. But we introduce precompiles to help speed up the execution of StarkNet, because that really needs to run fast. But the language is general purpose, and we optimize for that to run fast, both on client side and for general smart contracts on Cairo. There's no, on StarkNet it's not.
If that was true, you wouldn't need the precompiles, because it would be fast enough.
Fast enough, well, fast enough is not a well-defined notion.
But if it's not fast enough for you, why is it going to be fast enough for anybody else that's consuming your VM?
First of all, it is because it's different scales. If you run a small program on your computer and you want to prove it for your specific small-ish application, then you can do that and it's good enough. If you want to run a server farm to be an operator of a closed network, then you can invest in precompiles or built-ins or whatever you want to call it, or codes that are good for you. You don't have to. I don't see it as a being. I don't see why a purist approach to this is the right choice.
I'm exaggerating what I'm saying because I'm saying it doesn't scale, and you're saying, well, if you want to write something small, it works, but if you want to write something complicated, it doesn't.
You also, when you want to write like to train a huge LLM, then you could say, okay, my GPUs don't scale on my computer,
Yeah,
right?
but
But
it's
need a server farm to run it.
yeah, but you don't. But you need to reach the precompile box far before you get to scaling further.
Yeah, go for it, Jacob. You want to add something on precompile?
Yeah, I think a nice thing right now is you only need like 8 precompiles, and some zkVMs have already written it. I will preface that with we're pretty much just proving EVM like state transition functions. I do think the work that Powder Labs is doing here with auto-generated precompiles is very interesting. So they're making it to where you like write a general purpose program, and then I'm gonna butcher the actual architecture so bad, but like they have a compiler that can like sort of generate a precompile for you that then goes in a general purpose zkVM, which I think is pretty dope. And we're definitely tracking the work they're doing over there.
I mean, do you want to add something?
I was going to mention the auto precompile as well. I just think one, it might be like a eruption of AI, but also explain why there are so many zkVMs out there. I think there are like 25 zkVMs, but there's really like 3 or 4 architectures, maybe 5, and then adding little twists to it. So you can add twists to the proof system, but you can also add twists to maybe the precompile. So I agree that it's not scalable. If you see precompiles or adding new extensions to your ISA as a very cumbersome process of adding constraints by hand and having humans to do it. If you design some kind of DSL that allows you to, with a small subset of opcodes, create like strong locality like computations, kind of like what auto precompiles are doing, or maybe the Zergen or other languages, you could technically have more scalable ways to do it. And I have one question vis-a-vis Aztec. You guys have black boxes. I wonder if it's close to precompile or it's different.
Yeah, so it's a good point. The black boxes they are maybe slightly a little bit of technical debt. As in, you're right that they are close to precompiles. The idea is that instead of writing a little algorithm in Noir, the idea is like, well, our backend has like very, very optimized series of constraints that have been created that uses parts of our operating system that aren't exposed by Noir because they're complicated. So our goal is to remove those black boxes. And I do think it's different because at best they give you like a 2x speed up. It's not dramatic. You can remove them entirely. And I want to give an example of like the difference in scale of iteration between precompiles and a DSL with the ZK Passport team, because I was chatting with Teo and he was saying to me, oh, like the Italian passport uses SHA-1, which is terrifying. So they were like, we need SHA-1 support. So I'm like, SHA-1, okay. So I threw together a Noir library in 2 hours that did SHA-1. Job done, right? Because it's easy, right? You know, if I had to write precompile for SHA-1, like that's not 2 hours. That's like scheduling a sprint with a team on a progress board. And you know, yes, I will change my tune if tooling like Powder can get to the point where you can really do this stuff really effectively in a very natural way that an average Web 2 engineer can understand. But I think we're quite far away from that being practical, without like where Powder isn't adding in a lot of things that slow things down substantially.
But what if, sorry.
I wanted to add to that like, okay, for Stu now, we could go for precompiles for things that we had precompiles for Stone, such as Ketchak and Chateau, I believe. But we didn't. It wasn't worth the time to do it, so we just implemented them in Cairo 0, and now when you call it built-in for Ketchak, it's just Cairo code in our backend. So it's fast enough for StarkNet.
I was going to say, to your example of writing fast, like a SHA-1 library in Noir, to some ZKVMs, this would be considered almost a precompile because it's a constraint. And if
but what I'm saying is like, there's like no way on God's green earth you can write a precompile for a ZKVM in 2 hours and then just like ship it on GitHub, right? And then it can just be integrated into downstream tooling.
what I'm saying is, what if the ZKVM supported add-on with Noir, for example, and then they just treated it as a precompile because Noir compiles to a constraint. So you're saying, oh, today zkVM's engineers have to go to the low level and write the constraint for SHA-1 by hand to Stu backend. But what I'm saying is, in a world where people are looking into it, then it means that you would have your zkVM like RISC-V, and then like a Noir precompile library where you can add as many Noir code and just get bundled into your proof.
I mean, if you want to, if you're using Noir to like to do the messy work, then I mean, I'm all in favor of that. But the less you're going to look like a zkVM, the more you're going to look like a DSL. Particularly because it undermines the value prop of the zkVM. Because right now with RISC 0, it's write and Rust and it just works. If it's like write and Rust, oh, but you might utilize Noir as well, then it's kind of getting to what you're saying that these things start to become hybrids and the lines get blurred.
Yeah. Yeah, so I mean, like for context, for us to write a precompile with our DSL, transferred into a precompile in RISC 0. Which is pretty dope. Not ready for production and or releasing it to the public, but something we thought about. Like, I think I chatted with someone from your team like last ZK Summit. Definitely a thing you could do. We have a lot of work to do, so we won't prioritize productionizing that, but is a thing.
Well, I just want to add, like I've come across as having some strong principles here, but if zkVM start to integrate Noir, then I have other principles too, and I will sing the praises of your zkVM, and yeah.
Yeah, I mean, I think we already touched quite well on the precompiled aspects. Is there maybe any other, like, I don't know, angle, like differentiation ways, between these 25 zkVMs? So we kind of understood that precompiles maybe is one aspect. Are there like, we didn't really touch too much about like the ISA. So yeah, is it maybe the other big differentiation factor for zkVM? Yeah, go for it.
I would like to talk about a differentiation factor that people never talk about, and that is
Security?
not security. I think that's coming.
We
to
have
light.
to talk about it at some point.
Yeah, we do. But use cases, like personally, like if you ask me, like, is 25 zkVMs, too many? The answer is it's like just not enough, right? Like you need like custom zkVMs probably to do like custom use cases, and the problem is that like everyone's pretty much just proving ETH blocks right now, and I would probably say 25 is a little too much for that single use case. Yeah. But like very interested in client-side proving with like something like Noir or Maiden, or doing like web proofs in certain ways. I think that's where we need differentiation. Less talk about like custom ISAs and stuff.
I mean, yeah, I guess customized ISA is a mean to an end, the end being the different use cases. You want to add something?
I want to build on what you're saying and say that asking whether there are too many zkVMs or should we use customized. Like typically when you start building something, you have a purpose for which you're building it. And I feel like maybe this is kind of what's lacking a little bit. So everybody knows that this, for years, everybody has known that this is groundbreaking technology, like the ZK proofs, and finally blockchains are a use case. Okay, we need to use ZK, but there's still like a little bit of a sense that people don't know what they're building towards. And I think we also, of course, at Starkware had these considerations, and at some point you pick a direction and you have to optimize for this direction, even if it means that your zkVM isn't necessarily optimized generally, but it's optimized for what you're doing and you have a purpose in mind. So I think that's
I mean that makes sense. Yeah, you want to add something, Jacob? Go ahead.
For use cases,
I mean, ReZero was the first one.
Yeah. But like iStack's focusing on privacy. Y'all are focusing on like client-side proving. I think some people are focusing on like web proofs. I think that's really fascinating, right? I think the reason why I personally work on ZK is not to prove Ethereum blocks forever. I think one day, right, ZK is like as important as key pair cryptography. So let's start diving into Web 2 stuff and like talking to big tech companies and okay, what do you need? And let's optimize for that. I think one example is we had chatted with like a big tech company that wanted to generate proofs on an iPhone. for like RSA signatures. So we actually like forked RISC0 and then made like a much more custom thing. And we actually got it to like a decent time. We could generate an RSA signature in like a second and a half. But it's like a like a heavy fork compared to like what we let people use today.
Yeah, I mean, too few, too many. It really depends on on your lens, right? Are you looking at it from a product perspective? Are you looking at it from an ecosystem perspective? If I was dictator of the universe, I wouldn't force these teams to use fewer zkVMs.
Very kind of you.
You're very welcome. But that being said, I don't think it's wise. If a new team comes up and they're like, we're doing a new zkVM to prove EVM blocks, then it's like, great, you're gonna die. But yeah. But their contributions before they die may be useful and incorporate into other things. So it'll be useful in that way. And I mean, it's evolution, right? It's natural selection. Like every species is exploiting some kind of ecological niche, and if you have two species exploiting the same niche, and they're undifferentiated, one of them will be better at it, and the other one will die and go extinct.
Because there's more competition.
Yeah. Yeah, I think what needs to happen is, that if you have a custom VM, like it needs to have a purpose that's unique from others. It needs to serve some kind of unique value proposition. That's not really the case right now with the 25 zkVMs, but that'll shake out soon enough, right?
I can give a wish list for. So I think 25 is a good number for us to iterate and exchange. For example, the Zisk team, when I saw Polygon was building on RISC-V, I was like, another one. And then in a few months, they came up with a way to 10x trace generation speed. And everyone was like, oh, okay, we have to incorporate this. So I think in some sense, and at the beginning when Succinct forked the RISC-0 toolchain, people were like, they're forking, it's open source, but it's forking. But then they came up with the jagged polynomial and the hypercube, and then they proved the theorem in real time, most of the blocks. So I think it's quite nice. And as a community, at the beginning, we're very tribal. Towards the end, we're saying, okay, everything is the same thing in some sense. Because now people are agreeing that you probably want to compile from Rust or some high-level language. So for example, Maiden started, they were a very custom zkVM. Now they're saying, okay, guys, we're adding WebAssembly modules. So we want higher level language support. Same for Petra. Cairo, we're thinking about being able to compile higher level languages as well. So that's one thing we kind of agree on. We say, okay, high level language is good. Custom stuff, you guys have Rust, but your recursion is coded into your DSL. So we agree that DSL are good. So I think, high level language is a must. So I think people are going to convert to this. Custom optimizations for recursion, and then pushing the research field.
So I think I want to add that high levels are good for end developers, and lower levels are good for speed and performance, and that's okay for them to coexist, because some people want to drive performance and some people want stuff that's easy to do in a short period of time. But also I want to say that the ETH proofs race, it has very good aspects in the sense that it seems to be driving the technology forward, but it's also, I fear, kind of like everybody overfitting their models to a single data set. So it's kind of, in that sense, maybe biasing the whole industry towards a direction that might not be that interesting.
So are you guys all agreeing that Justin Drake is basically coercing you to prove Ethereum block, and that's, I mean, is it good or bad?
And it's not causing me to prove Ethereum block.
He's not there, he's not there.
Else, honestly, peak mindshare for ZK was probably 2-3 years ago. That sound about right, Zach? Like when it was super hot.
I mean, it's pretty hot today.
Yeah, I mean, we're trending up, and I want ZK to be the hot thing, and the only way that's gonna be is everyone is making advancements, and we have a really nice crew. Big.
Today, not in the same way it was, because there's less of a focus on the tech and more focus on what can this tech actually do, what are the products that you can build with it, which I think is completely appropriate. And I think it's no longer interesting if someone's like, my zkVM is 10% more performant than the other one. Great, good job. What can you do with it? Yeah.
I think also 2 years ago the fight was Circuit versus zkVM. Today it kind of sounded like zkDSL versus zkVM, but I think we're past that to some extent.
Yeah. It's not even a fight because it's like we have different like all the
Different
use
trade-offs
cases,
and
and
use
like I
cases,
wouldn't
yeah.
expect like an L2, a transparent L2 to use a DSL, and yeah, like I'm not genuinely. If I was proving EVM blocks, I wouldn't use a DSL. I'd just use like RISC-0 or like Fork2 or use SP0. Yeah, it's just every niche has a different way of exploiting it.
But I think one cool is can you prove on the edge devices and local proving for privacy, but even for decentralization to some extent. Because maybe the overfitting, so I know it might be temporary, but the overfitting of the ETH proof challenge are pushing people to have data centers to prove Ethereum or blockchain. I think it might be interesting to look into zkVM plus client-side proving stuff. So that's also what we're doing right now. So in the land of Cairo, but also Stu. So what if you could prove Ethereum, but just one CPU, one GPU in real time?
Let me do it in the browser.
Yeah, in the browser.
Yeah. I mean, yeah, like I agree with you. Because we've been focusing on very different things, where like the narratives around the L2s are like we've been living in a parallel dimension, right? Where for years the been okay, right? That's 5 secrets in it. What do you do? And so like everything we've done is tailored towards client-side proving. I mean, it's to the is completely different. Our ZK stack is completely predict the future. Future will probably trend towards the like error correcting codes, 32-bit prime stuff. But today, if you want to do client-side proving today efficiently with low memory, I think we made. So I don't want to be arrogant. I think we made all the right choices because like today, like take ZK Passport. It's on the App Store. You can download it right now. Like go to the App Store and download ZK Passport, right? And it's using ZK proofs client side, and it's really fast. So yeah, I think there has been a huge amount of overfitting, and the ecosystem has suffered a little bit because of it.
I want to say that I think our stacks are not that different technologically. Right. Look at them. Not that different.
I mean, conceptually probably not, but like in terms of implementation, right? Like if you're doing error correcting codes versus ECC, if you're doing 32 bits versus 256-bit, like it gets really messy.
Like if you read it in papers detailing what you did, these are constants, right?
Listen, if you want to put a PR into Brettenberg to add Stu, I'm all in favor of it. It's easy. You should do it. 20-minute job, quick. Yeah, it'll be really quick, really quick.
So there is one thing I want to talk about. I had this maybe talk about benchmarking, but actually instead of benchmarking, I want to talk about the thing that most people don't talk about, which is the security. So yeah, I want to hear you guys talk about how you contemplating that problem. Like how do you make sure that there is no iceberg? How do you for that? Maybe we can talk about form verification. So yeah, I don't know. Maybe Jacob, you can start with that. And yeah, I'm curious to hear about rather than comparing the performances and which is faster. Oh, mine is 10% faster. Like
Yeah, I mean the tech is new. There will be bugs. I think a big point is like how are you going to deal with bugs and how are you going to constantly check and have robust pipeline? Like security is always a journey. It's never a destination. You're never there. The current state of security in some ZK projects saddens me at times because I think a large bug is just going to hurt us all. So I would hope that we hold each other. I think if someone would have done a trusted setup ceremony 3 years ago and only had the team members do the trusted setup ceremony behind closed doors, they probably would have gotten called out on Twitter pretty hard, but we don't do that anymore. So yeah, I think there's great work. 20 mil up for grabs right now for formal verification if you're looking for work from the EF. There's a bunch of cool tools. Happy to work with anyone on that. We have a few tools right now that are actually in production. One's called Picus, where actually CI now we check under, which is pretty dope. Yep. Shout out to Veridis for building that one for 6 months,
Mhm.
which is really cool. And then I think we're just lucky enough to have formal verification experts. So working on that. I think, could we get to soundness formal verification, which of course you assume that the, tooling is correct as well, in the next 9 to 12 months? Honestly, sooner than that, especially for under constraint bugs. Yeah, I think completeness is going to be a whole other beast, which is really difficult. We're not too worried about completeness for EVM blocks specifically. Our zkVM tends to be pretty memory efficient, and like all of these prover killers, we don't really have any problems with. But hey, if you want to push, yeah. But if you want to push gigagas, then like we might run into some problems.
I just think if you can, you should adopt a very pragmatic redundancy. So if you can, you should get multiple provers that rely on different backends. We saw that 2 weeks ago, there was a bug in Plonky 3 verifier. I think it was critical or high. So if possible, at least 2.
Yeah.
So that's just for the maybe blockchain or high security, just redundancy in the prover. And as you mentioned, formally verification. Sorry. There's fuzzing efforts from the EF as well. So fuzzing. So I wanted to say multi-layered approach. And
Yeah. Do you want to go?
I just want to touch on the completeness because, like, for us, this is a problem. Like, we have Sierra for this, so people can't write smart contracts that can't be proven in a block. But even after that, we now are implementing Stu. We're testing in production. We have to make sure that, okay, there's no smart contract that's not provable. We have to make sure a block is not provable. Not provable. So, it's a thing that we've been working towards for a long time, and we are very aware of, and we feel like that there's maybe not enough discussion about this.
Well, I'd agree with that. I think that the state of security in the ZK space is very primitive largely because of the centralization. Like right now, all the ZKL2s, right, like the provers are centralized, the sequences are centralized, right? Like where basically the entity building the tech is running the sequencer. And so if there is a bug in the prover, it's not going to be catastrophic because that bug is not going to be exploited because you kind of trust that the people who wrote the tech are good actors, and they're not the Lazarus group. For Aztec, the incentives are very, very different. It's a different kettle of fish, right? Because we are decentralized. We launched our testnet decentralized. We will launch our mainnet decentralized. And so if there is a bug in our prover, it can and likely will be used to steal funds. It's not something where like, oh, well, we're centralized so we can protect. And so for us, security it's the existential fear that keeps us up at night. It's not a nice to have. It's not a branding thing. It's a need. And so I can talk a bit about how we're doing security. Like there is no silver bullet. We're Noir is now starting to audit. We're basically triggering our code freezes. We're triggering our audit cycles now, where we're doing very rigorous internal audit processes. Where the idea is, if the people if you wrote a library, you wrote some code, you're not auditing it, you audit something else. We try to be very rigorous there. After the internal audits, we do external audits, ideally more than one. And we have different auditing agencies for different parts of our code base because it's there's lots of different domains across the whole tech stack. And then we have obviously a very generous, once we're live, have a very generous bug bounty because ultimately you need eyeballs on this thing. We aren't going to launch without any bugs. It's not possible. It's never been done before, and we're not going to break that trend. What we want to make sure is that we can lean on and rely on our community because the community in Web3, it's full of white hats, it's full of grey hats, it's full of people who will do the right thing, particularly if they're richly rewarded. And we're still in this window, right, where the people who actually have the domain knowledge to identify and exploit cryptographic bugs are typically within the industry. They're domain experts. They are high integrity. That's going to change. I imagine there's probably some very, very poor, brutalized North Koreans in a basement somewhere, like reading up on Plonk and Stu and finite field arithmetic. Yeah, what is Goblin Plonk? Yeah. I'm probably psychologically torturing a couple of North Koreans right now. So that will change. But right now, we have this small window where we really need to lean on our community to help us find these bugs. Also, with our release, we're structuring our entire release cycle around security, where we're focused. Our first mainnet release, we're calling it Alpha, where we're going to be very explicit about the risks. We're not going to be like, YOLO money, and it's great, it'll work. No, we're going to be like, this is bloody dangerous. So it's very, very dangerous. Only like you're putting your funds at risk. Expect relatively frequent hard forks as we've patched things, and then once we basically have a checklist of things that need to happen. For example, like no serious or critical bug reports for 3 months. 99% block uptime. And once all these pre-flight checkpoints have been hit, then we'll be like, okay, now we're going to move to beta, where things are going to be a bit more stable and secure.
How will you know if someone has exploited a bug if the state is private? What if someone just spends a node and mints some token and you will never know?
That's why I said in our communication, we'll say expect hard forks, because if you find a bug,
you will social consensus that person out of the...
Well, no, you literally do a hard fork. You're like, okay, well, like we're like trying to have to migrate everything across, and then at least in the migration, right? If you basically have to, if migrating between hard forks, if you have to turn your private state into public state, then at the very least you identify if an exploit has occurred.
Okay.
Pardon?
Like a guacamole.
Very aligned with Ilias. I think multi-prover is going to be very attractive, right? Currently, to run like a ZK rollup per month is like $3,000 to $4,000, which is starting to seem like people have the appetite for this. And as we do like another 5, 10x, I don't know, 15x in performance towards the end of the year, like doing multiple proving systems, I think is really cool. Very much respect y'all's approach to security. And we have the same problem because Boundless is launching in like a few weeks, and it's fully permissionless and fully decentralized. And like once I click the button, we can't stop it, which is like dope and based. I hope the market cares. But yeah, we have the same problem. I think we made proving permissionless on Friday on testnet. There's already 30 provers. I do not know who they are. So
I'm good. I'm glad you're taking those steps.
Yeah, I want to say that like a lot of what we're doing now with Stu is preparation towards decentralizing our proving. So Starknet version 0.14 will be the beginning of decentralized sequencing. So it will be us. We implemented the entire stack to have things decentralized, and we're going to run ourselves several sequencers. And the next step would be to decentralize all sequencing. And after that, we want to also decentralize proving. It's a different layer, so it adds a different layer of complexity. But this is why we are formally verifying all of our errors, auditing everything internally, externally, and of course, bug bounties, everything. And it is terrifying, right? But you have to somehow accommodate it, yeah.
One thing I forgot to mention is also we do a lot of fuzzing. Like fuzzing is amazing. Like the amount of bugs that we found with fuzzing that we would never find by looking at the code, it's really impressive.
Yeah, we actually, our approach to fuzzing is just to, like with Stu now, we just mirror our mainnet and like test everything mirrored, and then you find a lot of things that you didn't find.
So I think we're approaching time, more or less, but I want to have a last round, coming back to the topic 25 zkVMs. So just have your estimation or take a gamble. Maybe we come back in a couple years here and we look at at your prediction. So I'm wearing a Sysmo shirt today. That's a dead company. So how many zkVMs are going to be dead in 2 years? And maybe is the number of zkVM actually going to be higher than 25 or lower? I think the conclusion of our discussion is like it kind of depends on the use case, I think. If it's only about proving Ethereum blocks, 25 is too many probably. But if you find other use case, which I think in this room we all hope for, it makes sense to have actually more than that. So yeah, starting with you, Jacob. So 25.
Companies or teams or research teams?
Go for it, whatever. I just want some gambling guesses.
I hope none of them are dead and we retain the talent that we have so we can continue to advance at the pace we're doing. I think it's really nice. if I had to give a prediction, I think half will probably die. But at the end of it all, there will be more zkVMs than there are today doing more and special things, which I think is just
How
super
many? I
exciting.
want a number.
I have no idea. 50? We have to convince VCs to invest in ZK Tech again.
They kind of did already, but yeah.
Yeah, I think I don't know how many are going to be around, but I know there's a trend basically where the majority of use case is going to concentrate in a very small number of zkVMs, and the absolute number of zkVMs will probably still increase. A bit like how many Ethereum variants are there? If you look at all hard forks, like there's thousands, tens of thousands, right? But how many are actually used? One. So similarly, zkVMs, maybe 3 or 4. And as for what will die, what will survive, I can make no predictions other than in 5 to 10 years, Aztec will still be around. We are like a cockroach.
Okay.
You can't get rid of it. Been here 8 years.
Wearable guess. Okay.
Win the next, mega goblin plonk paper.
Post-minute when I have some time to do research.
Can you call it Urukai or like?
Possibly,
So I don't know if I want to guess. I hope like there will be variety to match the use cases. Use cases, and definitely I'm all for it. Yeah.
Yeah, I mean, we all hope that's the case.
I guess in terms of companies, I think less. In terms of libraries, we're going to see tons of flavors as modules. My guess is that some of the teams you see in the ETH proof list, not all of them are incorporated companies that try to make a profit. Some of them are research teams, so they'll get hired probably. No, I mean, I think probably more like 10 incorporated companies doing zkVM stuff.
Okay, I have some guesses, so yeah. We'll get the recording. I think it's going to be more. I mean, again, I think we all hope here that ZK is going to get adopted and we're going to find new use case. I think the Google initiative with their wallet incorporating ZK is kind of an example. Some people in this very room working on ZK passport, stuff like that. It's also a way to have another use case for zkVM other than proving Ethereum block, even though Justin Drake is a great guy, but there are other things you can do with ZK. So yeah, no, I hope it's going to be more. I like the 50 prediction in terms of how many zkVMs there are. Maybe it's not 50 companies. Maybe it's like 1,000, like Ethereum, I don't know, roll-ups. The thing is, if it's 1,000, probably only like 1% of them are actually used. So I don't know if it's a good thing. I like 50 because it's big, but it's not too big either. Sometimes when it's too big, it means nobody's actually using it. So.
I can make a spicier prediction actually, which is that I think so. Pardon? No. You gotta have faith, man. You gotta have faith. No, it's that a lot of what people are imagining, like diverse zkVMs are going to be used for, is actually going to be gobbled up by Noir, because Noir is it's backend agnostic, right? It's not just an Aztec crypto thing. World is building a backend for Noir. Several others in the works. Like you can verify Noir proofs on Starknet, and so I think that for a lot of people, if you're not doing things like proving L2 blocks, if you want to do something client side, if you want to do something real world, well, I'm very biased here, extremely biased, but I think that Noir is going to be quite a natural language, and that in 5 to 10 years, it won't be viewed as a DSL, it'll be viewed as a language like Rust or Golang.
I think that will be Cairo.
Game on.
I thought you were.
Everybody's
doing ZKVM,
biased.
so you don't count for the bet.
No. I'm just saying that what the panel here thinks will be zkVM, so actually going to be eaten by Noir.
I have a prediction that in 24 months, and this is not based on any insider information, in 24 months, there will be a big tech company using RISC-0 on an iPhone to verify proofs for privacy.
RISC-0 on iPhone.
24 months. What? Game on. Yeah. Happy to compete.
I think that in every bet there's one liar and in every bet there's one cheater and one idiot, and if you don't know who you are, then you're the idiot. So I'm not going to make any predictions on this, but yeah.
This is gonna be
That's a good one.
I think it's a great conclusion to this panel. Thank you very much, guys. You made my work very easy. And thanks to the organizer.
Same
or they are like blood enemies, and
Yeah,
they
exactly.
literally want to kill each other.
Well, we're
So there's
vegan.
nothing in there's nothing in the middle.
It's quite rare.
But
It's quite.
it's very rare. It's very
Yeah.
rare.
I think we really internally like. I mean, Jeremy and Frank started this thing like to do client side proving, which is like, oh shit, the funding allows us to extend the credit away for blockchain and stuff. Like, there's some. I mean, just on like a personal level, also like this stupid Coinbase thing. I'm getting like letters. Coinbase had a really large leak a few months back, and they didn't tell anyone. I personally am receiving letters with like my personal information at my home, and like that is like really scary, especially considering
The attacks, like the France,
yeah, and like they didn't disclose it for like 6 months, and like
No, they have to. It's why client-side data is important, right? Like it's why we want to create systems where tech companies they don't need all that information.
Do you guys ever go to like any like of the open source cryptography conferences or like the Open Internet Standards conference?
Not instruments. We avoid the cryptography ones because it seems generally it's either a bit too low level, B they we should obviously go to the internet.
You should really. So we send a large delegate of people to open source cryptography conference. I think it was in Bulgaria or somewhere a few months ago, and then the Open Internet Standard conference. I think you would very vibe, but like maybe some of your developers, like I mean, these people are literally talking about like we went from HTTP to HTTPS. They're talking about the properties that is literally HTTPS, and like they're like considering like talking about like these standards and integrating these systems. It's definitely start showing up on this.
I think for us we've always wanted to kind of like speak with actions, and like when we have like stuff we can show as opposed to like hey, this would be good, and like really good stuff. Now we actually have some of that.
Can you guys run in GPU or web GPU?
That's the next. That's post mainnet. Once we have some resources for it, it's really hard to make it perform with CPUs because you only have like 100 megs of RAM or something like it's
100 to 256. But man, that's the golden odds.
It is.
Even if it takes like a minute to generate the proof, like it's still acceptable in like a wide range of use cases when we talk to people.
Yeah, totally. And also the thing that we're quite bullish about longer term is TE proving, to be honest, because really, TEs are terrible if you want to store secrets long term. If it's holding data for 30 seconds.
Ephemeral is fine.
That's what
Funny enough, like
that's what TE proving is.
Jeremy used to be a principal engineer on SGX.
Yeah.
Like it's horse, like words like came back from like war, like talking about it. Like it's millions of lines of code. It's tens of thousands of engineers that don't talk to one another, and this is why you get random side channel attacks where it's not even people understanding the code base because it's all closed source, which is another red flag. It's just because people can like prod it and like get things out. And it's brutal. Maybe Nitro's a little better.
Maybe I need to change my assumptions, but I'm assuming like
Also, there's a reason why
30 seconds maybe.
Also, like, I mean, there's a reason why the government funded them and then never used them because government doesn't meet the government spec for
I know, but
security.
I mean, yeah, but that doesn't. I mean, fucking up that would be government spec because this is
Yeah.
so
Government used to be less now. Yeah. They use it in like government agencies and like
but they whinge about like it goes and they all everyone needs to be responsible.
That's only for like secret sharing. You can use it for anything.
So they're probably telling us on a PNG platform.
Yeah. Also, like, what is post quantum?
Yeah.
Oh yeah, we totally.
Yeah.
So you mentioned, is there a point where you write many lines of code and the number of gates explodes?
Yeah.
Well, it depends on how you write it, right? Like, because it doesn't, we don't, because there's no native non-determinism. Like, if you're doing branches, then that will, if you do like branches, if you're doing it in a certain, like, specific ways, then the compiler, like kickstart, like, for example, yeah, and then you'll get some big complexity. But normally it's pretty linear. So yeah, eventually, you write it up, you make your library long enough, and you'll run out of resources. But that's where recursion comes in. Generally, the thing that we find the challenge with R is that it's very easy to learn it. It's relatively tricky to write tightly optimized R because you basically have to reimagine your program as a state machine.
You can have a compiler bug.
Very heavy. It's a bit like old school computing in the 80s, where
LLVM has had a bunch of bugs.
minimize the amount of
thing is
doing,
that
and
like
you try to represent non-determinism,
like
five
think about data
data
representation, trying to mitigate risk.
and that's
There's
not
so much
very
fun
intuitive.
to make that
So
ML
we're
be
trying to think
more
about
and
how
more
to steer
secure.
this.
So I'd much rather take Facebook.
This only
money,
really raises its head
you know,
at
spending
like
15
low-level
million
libraries.
on LLVM.
So we're just trying
So
to
you're
like
saying
get
like
a
you're
core
saying
low-level libraries.
your input is the
I think
binary.
that's one of
Yeah,
the
but that corresponds and
attractive
also the
aspects
program
of
that you
Exactly.
is that
not
at the web you don't
Exactly.
actually
So
know
yeah,
where
our
your
input,
program
because we made a
is
CPU, is just the RISC-V bytecode.
continuation.
So like the bug attack would have to be like an exploitable bug, which we
Eventually,
control
absolutely.
compiling down to
The
something
zkvms
else.
for the
And like
seven
to make the binary
Yeah,
Reading
which is something that
yeah,
we're
reading the
honestly
binary
with the ASIC network.
So the
This
attacker
kind of
would
gets
have to see
simplified a lot.
because
If
you
you're
as
building an up, you're writing a
requester
project
are
to
going to generate
an
all
ASIC because
right?
every
So the attacker would have to see
well, every external
different
function
if it's
is
the bytecode
it's
input you chose
exactly.
as an
So it makes it a
application,
bit easier
because
to
we
sometimes
specify right, the
yeah.
action and program.
have any like
Yeah,
downstream
you have to like find
messy
that,
code
oh, like
that
this
recursive
addition is now a subtraction and exploited by
But
being
yeah, there's so much that
Yeah.
there's so much that can be done.
That's
It's like
Yeah, I
so
see that.
that's a, it's like when we
But
think about
it's
But
frustrating.
imagine a scenario
I wish I had 100
like
active
that
systems.
has a committed,
binary or
committed
Not
binary.
everything, but
Yeah.
mostly the not just the
And
compilable
then users
tuning downstream.
use that by
The
generating
tuning downstream.
saying I
As
use
well as the
the program
Yeah, I
it
did
says
some
to,
action,
and I did some action and
Yeah, you
something
know,
else.
I wish
So
I could
indeed, you're right. Like they would have to update the binary following
we don't even use Cindy.
whatever.
Uh,
Yeah, saying this is not a
for
committed
WebAssembly.
binary.
any logic.
And it's at this point the attacker would have to identify the difference.
Yeah.
Right, so that might kind of help me because
Yeah, so when we think about
we're
Swiss
working on
cheese,
Stu right now and everything
that's
is
a lot of, that's a lot of
Yeah,
ways.
yeah, yeah.
I think with
Web
most,
honestly
honestly, the most
once you
people worry about right now
what is
is
any of 128 is like this
or like,
so it's rubbish.
like, imagine we're not following like this by
U32 times 16.
That's what we're
Yeah,
not.
which is
LGVM, people
Yeah.
bring
No,
a lot,
that's not
we're less
yeah,
worried
yeah.
about that.
so it's 4x.
And what about did you guys do
Yeah.
recursion in your process?
Yeah.
Like,
Why do you use
which way,
Rust?
which way do you do it?
Because
I read-
over local
Rust
why
is
do you
continuation.
choose,
but the
one way or
Aztec knows. I know
Aztec
they
knows
recurs
the
the local proofs.
Oh, so I
Exactly.
read
Yeah, so if I'm a user and I'm just like going to some website,
Okay, so
I don't want to ask the user to download
Oh, okay.
actually use this thing called continuation.
I would prefer
Where we
that
properly check that
the website
like one ends where proof 2 starts.
Yeah, well,
And then
you
we have
hit the
a
4 gigabyte RAM
it's a very
on proofs.
well, with our recursion, no. So on Aztec, right? Like that's because our circuits are limited to like 500 constraints. So you gotta compose.
The nice thing about
Got to
zkvms
compose functions
is
to
that
hit
like
that limit.
we are finding
I think it's like 2.5
bugs,
gigs, which
but
is
like
right now, which is something we want to work on because
Swiss cheese,
I
like
think
everything
taking the older iPhone
makes
will
finding
kill your browser time if you use it every
harder.
gigabyte.
Oh, yeah?
You really have to find like 3 or 4.
1 gig is rubbish. But yeah, like, yeah, like if you want to do concept ribbing, 1 gig is the real limit. It's not 4 gigs.
What's your take on this? Yeah, they work using like
Streaming is to be proven.
it's like more so we actually building like solutions jobs or reduction of the memory.
Streaming is very similar to filming. Like they achieve the same outcome.
Or Riesling or Sale, I don't remember.
Well, sort of. It's the idea is that the idea is when you're making your proof, you can like you need your witnesses. You need your witnesses to have something because it works.
It's actually
It does something.
But then you can generate chunks of your proof in a second. So you never need to make all the
So we're at
chunks,
like 99% code coverage.
which
And we actually check all of our precompiles as well.
but it's the same outcome, different effect, right? Because with the continuations, right, you have multiple proofs you're proposing recursively, or each proof you make it in its complete form, and then you hello.
There is Latin-based character talks.
Oh,
I think
sorry,
right
sorry.
now.
Okay.
You are welcome to join.
That is so-
Is it okay to start? Should I use the mic?
Mic check.
Oh, just for the stream. I see. Okay, okay. Yeah. So thank you very much for the for the invitation, and I'm very happy to be here to give a talk on what I'm working on, which are snarks based on lattice assumptions. So this talk would be light, so that you can you can enjoy the lunch or some food with this presentation. So it won't be super math heavy, and the motivations behind this research area. Okay. So yeah, I will need to ask Lisa to say next every time I go through the slide. So next. So okay, so so the outline for the talk is the talk will consist of three parts. So the first part will be the motivation for lattice-based cryptography, and the main motivation is basically post-quantum cryptography. So we will cover that. Then we will move on to the question, what lattices are, and then we will move on to at least give some overview on how to build snarks, and on the way how to build commitments, polynomial commitments, and so on. Okay. So I'm pretty sure everyone here is aware of that a lot of cryptography here is built on security of these primitives rely on some hard mathematical assumptions like discrete logarithm and RSA or factoring and so on. So next. Sorry. Yeah. And the problem is that or like the concern is that these problems can be efficiently solved by a quantum computer. So that's the Shor's attack. Next. Yes. So the question is that okay. So theoretically it's cool, but should we really care? Like, would they? Is this a real concern? And when would these quantum computers be built? Next. Can we go? Yeah, maybe you can like press so that it's faster, I guess. Yeah, so like many people probably have seen a lot of progress in building quantum computers by the industry leaders such as IBM, Google, and so on. And yeah, so there is this prediction that, so this study is from 5 years ago, so it may be even outdated by now. But yeah, so there is like a 5% chance that it can break classical crypto, but then 50% chance by 2050 to break RSA. Okay, so then here comes the natural question: if the classical crypto can be broken, let's say in 2050, so like in 25 years, then why should we care now, right? So could we move on to the next slide? So one of the main reasons is the standard harvest and decrypt attack, meaning that the adversary could. Is there any problem? It's okay. So echo 1, 2, 3. Where is it? Yes.
This harvest then decrypt attack.
Yes.
It only applies for, I mean, ordinary stars. That's we had a talk yesterday. It only applies for faking proofs, but assuming that your proof was supplied before quantum computers existed, then you're kind of in a safe spot with ordinary stars, right?
Right.
It's like it's a bit of a nuance, but.
Right. So obviously, one can find like.
Because you don't have like I mean a quantum break from the what is it for completeness. It's only for right for ordinary stars. There's a distinction, right? Not
I mean, yeah. So there's like specific examples where not everything is broken, but like so this efforts, this standardization effort that I will talk to is about like in general that we should move on. But like I agree that there are specific cases where like not everything is lost, but it really depends case by case. Yeah.
Yeah. But then, let's say in the blockchain space or even for the Ethereum community, you care about very, very specific cases. And then you should examine whether these cases are.
Right. Of course. So what's the problem? Oh.
I'm sorry, I didn't use Windows 10 years.
Do you want to just?
Yeah, I just need to put it back on like play. Perfect. We can go back to the timeline.
Then yeah, so like there are these typical arguments like it takes time to properly switch crypto systems if one needs to, or like in the case of from the research point of view, it takes time to actually design optimal cryptographic protocols. Next. So we can just press next. I don't want to like tell you so many times. Can you go next then? Yeah, right. So as a consequence, we've seen like multiple countries and multiple countries conducting like standardization efforts to move on to the post-quantum setting in general, like in cryptography. And like one consequence is that there is this NIST report, transition to post-quantum cryptography standards, which says that these well-known algorithms like ECDSA based on elliptic curves or RSA should be deprecated and disallowed after say 2035. Right. So then I mentioned this effort on standardizing post-quantum primitives. So the first step was to standardize signatures and encryption schemes. So could you? So then this comes to the question of what's post-quantum cryptography. So it is not quantum cryptography. So quantum cryptography is about cryptography which is run by quantum computers. Here in post-quantum cryptography, we care about the fact that we can run these algorithms on a classical computer, so like a laptop or mobile phone, but then the security should be hard, to break for both classical and quantum computers. Okay, and then in this landscape, we have multiple computational problems that people defined. Could you please, next? Like lattice-based cryptography. So yes, it's a lunchtime, so I put some food. So lattice-based cryptography, we have some hash. We have the hash-based cryptography, which is well known as well. Isogeny-based, code-based, multivariate polynomial, and even more ideas coming by the research community. So in terms of the standardization, which happened like in 2022, we have seen four schemes which were selected for standardization, which are like Kyber, Delphium, Falcon, and Sphinx, and 3 out of 4. So can we get the next slide? Rely on these lattice assumptions. Okay. Can we get the next slide? So I will discuss this in more detail, but like at least from a cryptographic point of view, people can see lattice-based constructions as nice post-quantum alternatives, thanks to some relatively small sizes compared to the other post-quantum schemes. Obviously, if you look at the, the group base or pairing base, then these are horrible sizes. And also, somewhat fast implementation because, as we will see later on, lattices, use a lot of linear algebra. So it's a lot of like matrix and matrix vector multiplication. So this could be parallelized and so on. So this comes the research question: if we can design, follow this strategy and design lattice-based privacy-preserving applications or snarks, and how they compare with other existing post-quantum hash-based snarks. Okay. So I just want to give somewhat a landscape of what's going on, at least from a research point of view. Yes, thank you. So I would say that this started, as expected. This was more of a theoretical theoretical work. So we have seen a few constructions already, 2018, 2020, 2021, which I would say were more of a theoretical side because, if one were to instantiate that, then one could get like hundreds of megabytes, basically. Thank you. So then, sorry, can we just, I think it's fine. So then it came, there was a scheme called Labrador, and now you can see that, the schemes get practical if you see that there are like names associated to them, or like acronyms, right? So then it started with Labrador, which was arguably the first one which actually produced like, real world, sizes, basically. And then later on in the coming years, so until now, people focus on actually fast verification, okay? And then, can we get one more? And then what we'll discuss, not really discuss in much detail, but then what's happening is that, the works which focus on fast verification, they lose on the proof size. So that's why they are a bit higher than the Labrador. And Greyhound is a little bit of a middle ground between somewhat fast verifier, but very small proof size. Yes, so now I want to move on to describing what lattices are very briefly, but any questions up to this point? Yes?
Do you think isogeny-based cryptography will come back?
So it's still, from what I understand, it's still going. Obviously, there was this, so that everyone's on the same page. There was this scheme called Psych, which got broken recently. What's interesting enough is that people are using this attack to break Psych to actually build some stuff. So the attack can be turned into a scheme, which I found pretty interesting. To answer your question, I don't. So there's definitely a lot of research going on to to understand the hardness of these isogeny-based constructions, and so I don't have a good intuition, but it seems that it's going. Yes.
So these schemes you mentioned, they have a trusted setup, right?
No. No. Transparent setup.
So it's a polynomial commitment,
Yeah.
lattice space
Yeah.
without transparent setup.
Yeah.
Okay.
So I think only like one of the schemes I mentioned has trusted setup. There was like a slab paper. I think almost all of them, definitely most of them have transparent setup.
And sorry, do you know also a vector, like a lattice space vector commitment with a transparent setup?
Yeah.
Okay, we should talk.
Yeah, sure, happy to talk. Obviously there are like different kind of criteria, so like, yeah. So this is the question that, appears when, like people ask me in a pub or people ask me in the family gatherings, well, what is a lattice, right? So it is not a lattice. So we can move on to the next slide. Yeah, so what is a lattice? Well, so here's a very, very simple definition so that, we can make this talk somewhat light. So let B, capital B, be a set of linearly independent vectors, let's say. Okay, so we can define a lattice with respect to this basis B to be just integer linear combinations of these vectors. Okay? So for example, so here are very simple examples like the lattice corresponding to this set 1 is just the set of all integers because all integers can be written as, like integer times 1, right? Similarly, if we have this set 1, 0, 0, 1, then if we take like all the integer linear combinations, then we get z squared. So maybe just, can we move on to the next slide? So maybe just to interact with the audience a little bit, can someone describe what this lattice corresponding to the set of just 2 is?
The even numbers.
Yes. So this lattice here is just the set of even numbers. And what about this one? Let's ask other people.
All integers? It's Z?
So here we're looking at, yeah, it's close, but like these, here we're looking at the set of like vectors of dimension 2, right?
Sure. Isomorph, so it's one-dimensional embedded in the
Right. So that's good. So basically, this consists of all the vectors which are some integer in the first coordinate and 0 in the second coordinate. So what are the problems we are interested in? Well, the most fundamental one, which which basically carries the whole lattice cryptography, is the so-called shortest vector problem. So in the shortest vector problem, we are given a lattice with some basis, and we have to find a short non-zero vector v, which is in that lattice. Okay, and when I say short means having small coefficients. For example, -1, 0, 1, minus, so between, let's say, minus beta and beta. Okay, so that's, I will denote it as the infinity norm being at most beta. So for those who want some challenge, then I can give you the exercise where we have this set 4 minus 3 minus 5. Maybe I can write it on the board. So I won't use the board too much today.
Maybe take the blue color.
Blue.
So V is the coefficients.
Sorry?
V is the coefficients that you have to multiply the basis by?
No. Actually, V is the out. So you want to find the coefficients. You want to find some coefficients. So when you sum up, it has ternary entries. Does that make sense?
So you have to find like stuff to multiply 4, 3, and -1, such that when you sum them,
It has.
smaller than 1.
Yes, exactly.
And for each line of V. Each
Yes.
row. Okay.
Right. Okay, so to sum up, you want to find lambda, some integers lambda 1, lambda 2, lambda 3, such that lambda 1 times 4 minus 3 minus 5 plus lambda 2 times 3, 0, 1 times lambda 3 minus 1, 1, 2 has minus 1, 0, 1 coefficients. And it's non-zero. Yeah, and then we can move on. Sorry?
103.
Ye-
Lambda 103. Oh, it will be 10 minus
Yeah.
1. Instead of minus 101.
Yeah, I think, yeah, there are like multiple solutions available, but yeah, it was just like a warm-up question. Yeah, probably 103 works. Because then the whole vector is 1, 0, 1, right? Like the, so 1, 0, 3, then it's, yeah, good. Yeah, so like in lattice-based cryptography, well, the question is, okay, so what type of lattices do we work with, right? So what we will work with in this talk are these random Q-array lattices. So you can think of these lattices as elements in the kernel of a random matrix A. Okay, so we consider vectors S such that AS is equal to 0 for some random matrix A. So then the SVP corresponding to this lattice is basically called the shortest integer solution problem, which basically says that given a random matrix A, find a short non-zero vector S such that AS is equal to 0 mod Q. Okay, so maybe the first question, if I remove the short part, then do you think this problem is still hard? So I
Put 0 everywhere.
if you
Short, sorry. I thought you said.
no yeah the short yeah. You can. Yeah, that's a perfectly valid point. So it can be, first of all, just all Qs. The second argument is that, you know, if parameters are chosen nicely, which is the case, one can just use linear algebra to find the solution.
How do you define a random matrix? And who provides the randomness?
Right, so it can be generated from a seed. So this is, yeah. Right. Right. So yeah. So when we talked about this transparent setup, it's just the transparent setup is basically to generate a bunch of random matrices. That's it. Yes.
There's no secret. Like, in the sense that if it's random, the randomness can be public. It's not like you have toxic waste at the end of your parameter generation ceremony. It's just that we need to guarantee that the distribution is uniform.
So the secret is the non-zero short vector, or?
Yeah, but that's a little bit like what you have in, how do I say this? That's a per person secret.
Yeah.
So you can configure your system with a one randomly generated matrix,
Okay.
and then everyone who wants a secret in that system can have a new non-zero short vector. So that everybody will share the same matrix.
Okay.
Yeah. Thanks. Yeah. So so thanks for moving. So yeah. So basically, we can think of lattice-based crypto as a combination of linear algebra, so some vectors and matrices. So here's the matrix, and the combination of together with shortest conditions. Okay, so I think it's a very nice combination of algebra and geometry. Next slide. Yeah, or just matrix-themed shorts. Okay, so for the remainder of my talk, I will move on to building commitments. Briefly about polynomial commitments, but yeah, I don't think there's much time, but yeah, let's move on. Yeah, so these are like pretty standard stuff. I guess everyone is familiar here. So we have interactive proofs. So we have the prover and the witness, and the prover wants to prove knowledge of a witness which satisfies some relation, and the prover and the verifier send messages to each other, and then the verifier says accept or reject. Then if the protocol is nice enough, then it can be turned non-interactive using Fiat-Shamir transform. So everyone, I'm pretty sure, is familiar with all that stuff. We can move on. Right, so then, just so that everyone's on the same page, when we talk about snarks, we look at the case when the proofs is much smaller than the witness, because if it was as large as the witness, then it could just send in the clear. And we are also interested in having a fast verification. Okay? What we will discuss, what we care about is this knowledge soundness or extractability property. So if a prover can convince the verifier with high probability, then the prover must know the witness. Okay, so or alternatively, the prover shouldn't be, a cheating prover who doesn't know the witness shouldn't be able to convince the verifier. So how to build snarks? So that's a very standard framework used nowadays, is by combining a cryptographic component, which are the polynomial commitments, together with an information theoretical object, which are polynomial interactive oracles of proofs, oracle proofs, to get snarks or zk snarks. So in the lattice setting, So in the lattice setting, oh no, there's the definition of polynomial commitment. Right, so that, again, everyone's on the same page. So what's a polynomial commitment? It's, you can think of it as one part is just the commitment scheme. So a party who possesses a polynomial of degree at most L, let's say, it can commit to it using this function commit. And interesting properties to us are, let's say, binding. So it's hard to find two different messages f and f prime, which map to the same commitment. And then we have hiding. If people care about zero knowledge, then the adversary cannot learn information about the polynomial from the commitment. Then we have the polynomial part, which is basically the polynomial evaluation proof, where the verifier sends the evaluation point, or like another party sends the evaluation point, and the first party needs to output the evaluation under evaluation of f under this evaluation point x. So f of x is equal to y, together with a proof that it has done it correctly. So the pi is the proof that f of x is equal to y, and t is a commitment to f. And then we have these standard, properties which are similar to what I described before, like completeness. For an honest prover, the verifier should accept. Knowledge soundness. So again, if a prover can convince the verifier with high probability, then it must know the polynomial f. Zero knowledge, succinctness, everyone is familiar with, I guess. Can we move on? So in the lattice setting, what's kind of interesting is that, like even building, more advanced stuff, it's easy if one can build just commitments with succinct proofs of opening. And this seems to be very hard in the lattice case. So I want to give some, brief overview why this seems to be hard. Even this step seems to be hard. Yes, can we move on? Good. So now let's talk a bit, let's talk about some proper constructions. So the first one is the ITAC commitment, which some of you may have seen it as lattice-based hash functions. Okay, so let's define ZQ to be the ring of integers modulo Q. And if I want to commit to a short message vector S of dimension m, let's say S is very long, like dimension million or something, what we can do is that we just multiply with this random matrix A on the left-hand side to get the commitment. Okay, so think of A as the very wide matrix with the constant number of rows. And to commit to it, you just multiply A with S. So that's basically it. And because the commitment is basically the number of, the length of the commitment is the number of rows, which I said is constant. Let's keep it informal as constant size. Then it compresses, the commitment compresses the message, of course. Yeah, so let me just talk about binding. So if someone manages to come up with two different messages which map to the same commitment, then we will have the equation AS is equal to AS prime mod Q. If you subtract, then you get A times S minus S prime equal to 0. And because both S and S prime were short, then S minus S prime is also short, so you've solved this. Sorry?
Are you saying it's impossible, or are you saying
It's impossible, yeah. To find two different messages which map to the same commitment.
why?
Under the
It's as hard as SIS.
Okay.
yeah. So under the
Because it
SI,
means that you have found a short non-zero vector
Yeah.
that sorts this.
right, which
So
should be
you
hard.
force some proof of work that is impossible to solve.
No, I mean if you believe that cis is hard, then this implies that binding of this commitment holds. That's it. Any other questions about the definition? About the construction? So one may think, okay, so I have this commitment scheme, why not just, I already have the commitment, why not just prove knowledge of this S, right? So the problem here is that the main issue is the verification time, because as I described, you can think of this matrix A to be very, very wide, right? And then if it's unstructured, then the verifier would, like in the process of verifying the proof, it will need to make, perform operations on this matrix A. So inherently, the verifier runtimes, the verifier would first of all have to read this A. So so this implies that the verifier runtime is linear in M. So that's not great. There have been some works which try to basically either add more structure to A to make the verifier faster, or use some pre-processing. Okay, and we will basically use this commitment as a subroutine to build a different style, different type commitment. So I think with our time, we will only focus on the square root, but this approach can be actually generalized to cube root, proof size, or even like polylogarithmic later on. Thanks. Okay, so what is the commitment scheme? Because I said that we won't use the vanilla I-type commitment. So the commitment scheme can be described as follows. So I have this long vector S, long in terms of the dimension, but short in terms of coefficients. And what I will do is, I said it's a square root approach. So I will split this vector S into chunks of smaller subvectors into square root of M such subvectors. So I split S into S1, S2, and so on. Then I multiply, then I commit to each of them using the I-type commitment. So I have AS1, AS2, up to AS square root of M. Okay? And then I get these partial commitments, so T1, T2, up to T square root of m. So this is my commitment scheme. And from the previous slide, we said that the commitment size is constant. So now we have square root of m constant things. So the commitment is square root. So that's the commitment scheme, and then I will move on to proving knowledge of an opening and why this structure helps. So any questions about the construction?
Do you have to pay a lot in padding if the message doesn't have a square root that is close?
Right. I mean, it's not really, well, how to say? I mean, you just need to add, more. Yeah, obviously here you can just add more, right? Some zeros or something. But I would say it hasn't been investigated in practice, like how much padding adds. It's still more like a theoretical side, yeah.
But well, regarding this square root thing, then you might pay security, right?
In what sense?
Because your matrix is smaller, so I could potentially break the SIS easier.
Yeah. So basically your SIS will be of this instance. So you want to break SIS for this.
Yeah.
And what we haven't discussed basically is that if SIS gets easier if your matrix A is wider.
What?
Yes, again.
The wider the easier? Or
The wider the easier.
to solve SIS?
Yes. Because if you can solve it for the small matrix, then you can consider the wider matrix and just ignore those, right? Sorry, you can ignore the columns, so then you end up with a smaller instance.
So in fact, you gain security.
Yeah.
But the width is n, no? Or the width is... the width is n.
So obviously, if you can solve SIS, like for this, right? Let's say A0, A1, then you can, if you can solve it for A0, then obviously you can set your solution to be S0 and this is 0, right? So this cancels out the A1.
Wait, so m can be ignored. It's not correlated to... Like, m is not part of the parameterized security of SIS. Only n?
Yes, it's n, yeah. But so technically speaking, there is some dependence, like
Minimal, like a min of m or something.
there is like some optimal m where the current lattice attacks for this problem seem to be, basically there is an optimal m for which the problem is the hardest based on the current attacks. Yeah, but very good questions. So why is this commitment scheme I described earlier interesting? Because now if you want to prove knowledge of, of the opening, it's basically this type of statement. I want to prove knowledge of some of some SIs such that ASI is equal to TI and SIs are short. Also what I wanted to say is that this square root of m is just, I just set it as square root of m, but there is, if you can split your vector S however you want, as long as it's of equal dimension, yeah. What I also want to highlight is that it's extremely important that this A, so you have bunch of similar statements, but it's the same A for all of them. And if you have different A's for each, I, then this solution wouldn't work. Okay, so this is kind of the template how the opening proof works. Well, it's actually very simple. So say the verifier sends some random some random coefficients, and the prover outputs the linear combination of these coefficients with these SIs. Okay, so the prover sends Z equal to C1 S1 plus C2 S2 and so on. And then the verifier just checks whether A times Z is equal to C1 T1 plus C2 T2 and so on. And then in terms of the prover message size, which is just Z in that case, the length of Z is the same as the length of each SI, which is square root. So in particular, we get like a square root proof size. But yeah, as already hinted here, there is a problem. So so the problem here lies with soundness, because I can define a cheating prover who doesn't know the witness and can convince the verifier. What's the strategy? Not really, but you can see that the prover knows SIs which are short, but if you look at this, this protocol, there's nothing about shortness, right? So how can we make use of it, as a malicious prover? Yeah, exactly. So if you don't have any shortness condition here, the malicious prover can just, which doesn't know anything, could just solve this equation and send the corresponding Z. So this leads to, sorry, can we get another slide? The second verification condition that Z should be short, okay, which would exclude this type of attacks. But then if Z is short, then Z is defined this way, right? So in particular, the challenges CI should also be short, because if CIs were large, then Z would also be large. Right? So this means that we should pick the challenges somewhat carefully. And so for the sake of simplicity, just say that these guys come from are just binary, 0, 1. Okay, so then for 0, 1, because the challenges are short, SIs are short, then Z should also have small coefficients, so this would be satisfied for an honest prover. But there is another problem here. So there is a cheating prover which can win with probability 1/2 without knowing the full witness. And what's the problem? So suppose there is a prover which knows, all the S, let's say S2, S3, S4, and so on, but it doesn't know the S1. What can they try to cheat this verifier without knowing S1? Oh yeah. I mean, but short. SY should be short, yeah.
They can just guess C1.
Yes. So in this particular case, exactly. So suppose I have this prover which knows everything apart from S1, and it will just hope that C1 will be 0. Okay. Because if C1 is 0, then this prover can actually respond without knowing S1, right? Because for C1 equal to 0, this vanishes. Yeah, so obviously one can generalize this attack by guessing C1, but yeah, so in particular, a cheating prover may win with probability 1/2. Yes.
How can, a prover doesn't know all the S2 up to S1?
I mean, so so we can call it, if we consider knowledge soundness, okay? So we can call we can call a cheating proof malicious if it doesn't know the whole witness, right? The whole witness is S1, S2, S3. So suppose it doesn't know S1, right? So it should be the case that without knowing S1, it shouldn't be able to convince the verifier. So the easy strategy is now to informally run this protocol in parallel. Can we get the next slide? So then we have the first invocation, second invocation, and so on. So kappa invocations of the protocol. So then the verifier sends multiple CIJs. And then for each first invocation, the prover outputs the corresponding Z1. For the second one, it sends Z2, and so on, and it sends kappa Z. And then the verifications equations are the same, but you do it for each instantiation from 1 to kappa. And then this attack that we talked about, you get the cheating probability from 1/2 to 1/2 to the kappa. Okay, so you can just pick kappa somewhat large, like 128, and you should be fine. So that's kind of the informal argument, but there is like a proper knowledge soundness proof for this. So then the prover message size is, you can see that it has to send many of Zs, so kappa of them. So that's why we have like kappa times square root of n, basically. So that's kind of the very brief overview of this square root approach. Right, so there are a few optimizations one can do to get much smaller proof sizes, because just sticking with the square root approach will give you, I would say maybe 10 megabyte proofs or something for large enough messages. So there are a few tricks, which I find interesting from a theoretical point of view. So now instead, what we've seen is that we had to rely, this protocol was over integers modulo q. But if we move on to, much more interesting rings, which are related to algebraic number theory, so if we run it over these polynomial rings, then one can get much better sizes. Okay, so in particular here, the problem that if I need challenges which are short, right, because that was one of the conditions, but we also wanted this challenge space to be large. And in this particular case, it's bad because, for 0, 1, there is this cheating attack with probability 1/2. One can come up with these nice challenge spaces where you don't have to repeat them. Okay, so the first trick is to move on from integers mod q to these polynomial rings. The second step is that instead of having this somewhat large commitment of T1, T2, and so on, one can additionally commit to these TIs to get even a single commitment, basically. And then the next step is that instead of sending this Z in the clear, one can prove knowledge of the final message, which satisfies the verification equations using the Labrador protocol. So this results in succinct commitment and proof sizes, and still square root verifier runtime. So what I wanted to say is that whether you can push this square root approach to cube root, fourth root, or even logarithmic, yes. So it is possible. So the idea is that when you have these commitments T1, T2, and so on, you will commit it further, basically. So you commit to these commitments, and then you build something of a tree, and then you kind of run this protocol that I showed you in recursion. But yeah, at some point in practice, this actually doesn't help. So maybe asymptotically, it's nice to have logarithmic verifier time, but in practice, what we can see is that it doesn't particularly give you good efficiency gains. Yeah, so this slide is about performance of lattice-based BCS. So the Greyhound that I talked about, for large messages or for large polynomials, it gives you proof sizes of around 50 kilobytes, which are much better than like other lattice-based schemes which focus on, logarithmic verifier time. Okay, but then, so there is this trade-off whether you want better verification or better proof sizes and so on. And comparing to the hash-based constructions or hash-based polynomial commitments, we can see that they can be somewhat comparable if we consider vectors of length 1 million. But here we're talking about like billions and stuff. Then we can see that lattices perform slightly better as of now. And this should be somewhat of a this shouldn't be a surprise, because instead of relying on hash functions, here we rely on on these assumptions which are very rich algebraically, right? Like it uses a lot of linear algebra. There's a lot of homomorphisms. So it should be the case that this, at least intuitively, that this rich algebraic structure should give you some efficiency gains. Can we get the next slide? Can the pre?
Can you repeat this intuition?
So,
I don't get it.
right. So the intuition is that solving lattice problems like SIS should seem easier than breaking hash functions, because of this rich algebraic structure of of lattices, of homomorphisms.
Yeah, I can give you a counterintuition.
Yeah.
Which I don't know what is true, of course.
Right.
I mean, hash functions have no transparent structure, but you can imagine like an AI detecting a statistical structure in hash functions, and so there is no transparent humans.
Right.
It's not clear that hash functions are easily or harder to break or easier to break. To me, at least.
Yeah. I mean, it may also be the case, but anyway, like these are like very active fields, and we have seen a lot of progress in in getting much more efficient schemes, for sure. Yes.
So this L does relate to the message size.
Right. Yeah. So, for example, the degree of the polynomial you commit to in the polynomial commitments.
Right. But you also have this Q. Can you also choose this arbitrarily,
So Q is chosen based on so you rely on this SIS assumption, and then the Q has to be chosen in such a way that the problem is hard.
What is Q?
Q is the modulus, the proof system modulus. Everything you do mod Q, right? So that Q, yeah. But just to give some intuition, you can think of Q being like around 2 to the 32, let's say.
That's enough for SIS?
Yeah. I mean, for SIS, it can be like, if you look at the NIST standardized schemes, it could be like 2 to the 16 or something.
Can you say about the prover and verify time in this table?
Right. So what I want to say is that at least currently with these schemes, we can see that the hash-based proof systems are much faster in terms of verification, with being like milliseconds or even faster than that. But for the lattice, in the lattice setting, actually, it's pretty bad. I mean, okay, so not really. It really depends how you define bad, but like it can be it can be like 1 second verification or 2 seconds. But what comes as a trade-off is the prover time, which for extremely large statements like 2 to the 30, it can reach around 40 seconds, which from what I've seen in the tables can be let's say around 2 times faster than the alternatives, hash-based alternatives. Yeah. So sorry. Yeah.
Going back to that table.
Yes.
So first, you can try it with different hashes, right?
Yeah. Right.
So which hash function is this table referring
So yeah, for the time, right? For
But if it's like SHA-256 or KSHAC, it's the same size of the digest.
But there's Poseidon, there's other stuff.
yes, I think
Works using arithmetic-based hash function.
You mean for verifier time or proof size?
yeah.
I mean, just wonder. I mean, I'm just wondering.
Right. So I think the sizes which were reported. So I think I took these from from various papers which basically implemented these, or like instantiated these. I think these were just based on like some SHA functions. Like I don't think these were like specialized for specialized hash functions. Yes.
Maybe a relevant question is, the lattice numbers, are they for like the same security level
Yes.
as the
Yes.
hash-based ones?
Good. Any other questions?
So lattice-based
Right.
the only motivation was also functions.
So there are a lot of other motivations, like the most popular way to build FHE is using lattices. And if you want some kind of verifiable FHE, then you basically have to prove some lattice statements. So yeah, if you want to prove that your encryption was done correctly, then you end up with basically a lattice statement, like a proving short S such that AS is equal to something. And then, like instead of trying to convert this statement, one can also use a lattice-based proof system to directly prove this lattice statement. Does it make sense? So yeah, so I guess FHE, IO. I mean, this sort of stuff is also the motivation for lattice-based cryptography. Yes.
And how is the field of research looking for recursion? Because if your verifier time is not like a log square, then you might have problems recursive.
Sorry, could you repeat the question?
No, if you want to do proof recursion,
Right.
how is it looking today in the research? Is it not yet at that moment?
I'm not super sure it's at that moment, like at this level yet. Yeah, so I think it's a very like early looking field. Yeah. Yeah. So basically everything I said. But yeah. So this concludes my talk. Yeah. Thanks. Yeah.
Who proved, not who, how was it proven that the discrete log problem was broken by quantum computers but not SIS?
So there is this Shor's algorithm in 1994, which can be adapted to proving discrete logarithm. For SIS, yeah, obviously it is hard to prove that that there is no quantum algorithm which can solve SIS. The kind of just a brief intuition why this, let's say why Shor's algorithm doesn't work for SIS is exactly this diagram that I have, like two circles. It is, the thing that, I guess secures lattice-based crypto from this type of attacks is this interesting combination of algebra and geometry. So, so because of caring about the shortness condition, it circumvents these type of quantum attacks that I mentioned before. But on the other hand, as not really hinted too much in this talk, this shortness condition also is a bit annoying in terms of constructing stuff, because when you add stuff, when you analyze parameters, you always have to keep in mind that all your secret components should be short, because this is the fundamental problem in lattice crypto. So in particular, if you add, like if you want to do, if you look at let's say folding schemes, I guess like this could be like a simple analogy. You have folding schemes, so in the lattice setting, you could just think about, okay, I have this ITAC commitment. I want to build a folding scheme out of it. That when you add, when you add your, let's say, your witnesses, then the norm grows, and it gets bigger, bigger, bigger. And then parameters have to be adjusted so that this, it has to be adjusted to accommodate for this norm growth. So which gets extremely annoying, basically. Yeah. Thanks.